have been was presented to South Africa. South Africa. No, they didn't not request me. And anyway, they somewhere in Vietnam or somewhere, and they would have difficulty to understand what I'm saying. But changing position, having changed my standpoint totally from the previous one. Previous one, I just kept the viewpoint of the skeptic, the skeptic clinician who does not believe anything and change anytime. But in this case, I'm going to become I'm going to pretend that so current situation of the nuclear medicine is beyond our satisfaction and beneath our satisfaction. So we need to just adopt some more. What here? Expanded ligands. So we are using ligands. And I'm going to just propose to you that we need to just pay attention to the achievements of our colleagues. I mean the chemists not belonging to the clinical department, chemists in the main campus, or the chemical engineers in campus or industry, especially in China and Singapore and Korea, not Japan, United States, and some the European countries, Max Planck, the Germany, or others. I don't think the Sweden is strong. I don't think UK. Yeah, UK is strong, but they're kind of the combination of the technology with nuclear medicine is in their infancy. So that's kind of a background and title on an advertisement. Now, so this is the one-slide summary of the recent progress. And nuclear medicine has reached this kind of recent success. In addition to previous success in therapy, what was the previous one? It might have been 50 years ago, the successful treatment of thyroid cancer. And then thyroid cancer practice was had prevailed to all of the globe. And everyone in any country has become the same level of expertise. The real shortage is just kind of a supply of iodine-131 or the shortage of the experts. Like in Nigeria, both are short. So I mean the several nuclear medicine physicians who were trained by the IAEA support in South Africa had come back to Nigeria, a huge country, 200 million population, so around the similar level here. But they could not find the radionuclides imported from the outside, and also they could not find the facility, despite the higher GDP of Nigeria. Nigeria has just kind of moved on from the low-income country to middle-income country. But they have changed their the specialty from nuclear medicine physician to family physicians. So no way to treat the thyroid cancer with radioactive iodine. So Akin Kunde was a previous fellow of my department, and he explained that in his country, if someone needs radioactive iodine treatment, radioiodine treatment, he or she needs to catch the airplane to fly to Ghana, the adjacent country. That's kind of a tragedy. And it's the same as in my country. Our patients suffering from the neuroendocrine tumor last year, 58 patients they booked the airplane and flew to the Kuala Lumpur at Beacon Hospital. Kindly, Dr. Lengeswaran Kasilingam, he treated the 58 subjects and came back. And 2 patients died because of the progress of the, according to Professor Kang, in my next room, our chairman, my successor, and he just sent almost 60%, 80% of the patients were sent by him. And according to his just casual explanation, while in the corridor, so he just 2 patients died, and 40% of the patients improved, and the another 60% are in just kind of a stationary disease or a little bit progressive. So he is planning the sending those patients again. So and according to the Dr. Seo's presentation, we know that we do gallium-68 the DOTA-TOC imaging. However, we cannot do because the Korean FDA do not allow, does not allow us to do so far. So we cannot do, and so there is no way to, but send the patients to Kuala Lumpur. So actually, why I'm here is just kind of to prevent that kind of tragedy for every patient. So how to achieve that is just kind of teaching each other based on our own the expertise and experiences. So neuroendocrine tumor. So that's the reason why I just put, unlike European experts, the slides, I put DOTA-TOC first. Why? Because it's approved. Actually, not approved. It's allowed in my country. DOTA-TATE and DOTA-NO. So if not, I would just put DOTA-TATE first, because the textbook is saying that. And castration-resistant prostate cancer. One of the faculty members in my country, he became the face of the castration resistance, the advanced stage. He's a neurosurgeon, one of the faculty. They try to persuade us to facilitate our research to adopt. However, we could not do the PSMA treatment. So finally, I heard, by just a rumor, he could find a way to reach Nanjing, to find Dr. Feng Wang of Nanjing First Hospital, and there they are doing this lutetium PSMA treatment. He's the member of the INET, European Neuroendocrine Tumor, and also his PSMA treatment is possible in Bad Berka and Melbourne, and also Nanjing, as far as I know. And also, interestingly, Pretoria of South Africa. I had been there, and Mike Sateke, Makaba Mike Sateke, he is doing the prostate treatment too, and radio. Okay. So, as a kind of outsider from the chemistry, that's my understanding or classification. As a ligands, we have used a small molecule and macromolecule, biomolecule, so such as the antibody. And then we have nanomaterials. During discussion, after Professor Yoon Sang-lee's presentation, I found that someone is using nanomaterials. So I'm not quite sure if there is an expert in nanotechnology here in Bangladesh, Dhaka, then why don't you just do that kind of research here? Before going into the diverse the classes of ligands, let me just explain. That's a small molecule. For the treatment of the tumor here, doxorubicin. When I was the resident in internal medicine, I used to use that, and which is also called adriamycin, which is cardiotoxic. And because of that, previously, 20 years ago, we did many the gated blood pool scan to find out the increase of the ejection fraction using gated blood pool scans. However, as I showed you, gated microspec scan is better than gated blood pool scan. It's a planar scan. Microspec scan is a tomography one. And cisplatin, here one of the cisplatin, they're using the platinum. And the etoposide, I have rare experience. Dacarbazine, so I could recognize those names. And temozolaimde, it's for it's a famous one for humor. And all those small molecules, so to my eyes, it's all, actually, I don't have any interest of conflict of these compounds. I do not belong to any pharmaceutical company. I am not a friend of the inventor of those that chemicals. So in my eyes and in your eyes, we have many benzene rings. So the outsider, we just even say that this looks like benzene. Why? Because it's a ring. Okay, it means that automatically hydrophobic. So it is the reaching every cell. The membrane is transparent for them. So in addition to the tumor, they just are distributed to everywhere. So she's causing here toxic, and not without off-target effect. In some eloquent, eloquent way, they say just a diplomatic way, not without off-target effect. So it means that here cannot eradicate tumor without killing human. However, they are using, our oncologists colleagues, they are using them. Then what about the tyrosine kinase inhibitors, IPs? So many IPs here. Nilotinib, imatinib, gefitinib, erlotinib. So again, you see many, not this one, you see many benzene rings and hydrophobic again. So they are using really toxic materials to save the, not save the children, save the people. So oncologists. And then, interestingly, with the advance of the molecular biology and biopharmaceutical sciences, it's different from the pharmaceutical science. Biopharmaceutical scientists, they are almost molecular biologists. Especially, they are one of the best, excellent molecular biologists who are doing a really good job. So they have developed here, Journal of Pharmaceutical Sciences here, several years ago. They summarized that those drugs are already used, those drugs are already having been, have been used for clinical purposes. Adenosine deaminase, L-aspartate is famous chemotherapy, the anti-cancer chemotherapy, and interferon here. Etoposide is just kind of stimulating bone marrow, and here GCSF, recombinant human one, and some of the monoclonal antibodies. The real, what is there are the real problems of those the drugs? You know, even though we are nuclear medicine physicians, we can't just sympathize. We need to sympathize the agony of the medical oncologists and the biopharmaceutical companies. Interestingly, the real problem was the half-time in biological fluid after injection. So half-time might be days. Do you think it's days? So who raise hand? The half-time are days, or hours. Yeah, so you expect hours. Me too. However, after reading this one, wow, it was really, the circulation half time was just minutes. So they needed to invent some method. They invented here PEGylation. All pegs are created not equal. Okay, that's the kind of viewpoint of the regulatory bodies, such as the EMA, European Medicine Agency, or the FDA, Food and Drug Administration. So FDA, no, polyethylene glycol is really biocompatible. It is causing immunoglobulin M response, IgM response. However, it's kind of a probability problem. However, the polyethylene glycol can be here, branched, can be the straight, or can have a different the molecular size, molecular weight. So everything is different, and the free part can have a SH molecule or the COOH, whatever. So how these molecules could be tagged with the polyethylene glycol and can be used for clinical purposes. It's just they have proven that it is okay, and also the circulation time has increased to hours. So we need to inject several times per day to treat the patients. That's another cumbersome. So that's the current status. So what I'm going to emphasize, if I say the conclusion first, nanoparticles are experiencing the similar problem, not unique problem. So small molecules have kind of a real toxic. And tyrosine kinase inhibitors, yeah, they are working without without alopecia or without kind of a bone marrow suppression. However, the kinase inhibitors, there are many signal transduction pathways, the detours. So immediately the resistance clones of the tumor cells are appearing. So our drug cannot compete the tumor's evolution power. That's kind of a Darwin win. Okay, Darwin wins, and we cannot. So that's the introduction. And there is another not frequently cited fact. Now you are seeing here. So by just how much would have been given for the gadolinium MRI study? They are using the contrast agent. Milligram. Raise your hand. Are they milligrams? A little bit larger than milligram. 1 gram. Raise your hand. Oh, you know that the large amount of the gadovist is given to the patients. You all know. You're well knowledgeable. So I did not know. I was just trying to make this the slide. I just kind of the package insert of the gadovist. I tried to find, and here 6 grams. You know, we just take Tylenol or oxycodone, just 500 milligrams. It's too much. But they inject 6 grams. Surprising. That's the reason why nephrogenic systemic sclerosis is happening. So, you know, the radiologists, they do know that. No, they don't know. Just that they do inject patient. So I'm really afraid of being just taken care of by radiologists. I really believe believe the medical oncologists. They are so strong. Okay, so I really believe in the interventional cardiologists. They saved my mother 10 years ago with a drug-eluting stent. They inserted 4, and still she's good with 10 the kinds of drug every morning and evening. So she's always complaining, and she's now at the age of 86. Okay, so really, but 6 grams. You know, here dosage forms of the NSPAT. NSPAT, what is NSPAT? Yeah, just a neuroendocrine tumor. Yeah, qualitative. So 40 microgram. So gram, microgram, million. Okay, and here non-pyrogenic tetrakis methoxy isobutyl isonitrate (MIBI). Just 1 milligram. Oh, it's 1 milligram. However, it's divided to 5. We can inject 5 persons. So 200 microgram, 100 microgram here is enough. So that's the situation. Okay. Magnetist. And then I just calculated how many materials, how many the molecules can be given as an exploratory investigative new drug allowed by the FDA. And first in human trial, skipping the small animal study, correct? Skipping small animal study. Rodent study, we can skip. ECD, for ECD, this is very important. Why? Because interestingly, rats and mice have circulating or the endothelial, I'm not quite sure. Anyway, vessel-related esterase, which is kind of chopping up ECD, ethylene cysteine dimer, immediately after injection. So no ECD can reach the brain. So if you just inject ECD, technetium labeled ECD to mouse, the brain uptake is void. No brain uptake. So you already know? No. So for ECD, they jumped up to the monkey study and then humans. That was 20 or 30 years ago. I learned that. I really was impressed. So they call it microdosing, first in human. So there are differences between the physiology. In physiology between mouse and human. So the microdose is defined as less than 1/100th of the dose of the test substance to yield pharmacological effect. If something is having the pharmacological effect, it's 1 milligram, then 1/10 is just a 10 microgram thing. And also should be 100 microgram or less. However, in case of the protein products, macromolecules, the microgram does not mean something. So they have adopted 30 nanomoles. So that's FDA guidance. And 30 nanomoles, and please be reminded that your high school chemistry, or if you're a genius, then it's elementary school chemistry, Avogadro number, and 10 to 16 nanoparticles or 10 to 16 protein molecules can be given under the allowance, I mean the permission of the FDA. That's legitimate. If something happens with the patients with that kind of injection, then you are free of responsibility. You are morally responsible, but you are not legally responsible. That's very important. So, in addition to protein products, I'm going to increase the dimension to nanoparticles. So, nanoparticles, it's 10 to 16 nanoparticles can be given without any. So, every day you are inhaling many nanoparticles, just like just like the inhalation study using carbon, the technetium carbon. So, yeah. So, or when you come out, so the pollutants are in the form of the nanoparticles. So why can't you use that amount, 10 to 16, too much? If public knows that, thank God the public does not remember the Avogadro number. So they are satisfied with the 30 nanomoles. They don't know the mole. And nano means a little bit smaller. 30 is just kind of 30, we can't just bear. So that's the one. And here, oh yeah, so that's the ridiculous. And this is the message here. You all know that the transarterial and both target. We don't know how to combine these to save our patients like EBRT and molecular radiotherapy. So that's the current situation. That's current situation, and we understand that. And final goal. I have used this second time. Used this slide yesterday. We do use the response evaluation criteria in solid tumors by CT. So here, I'm not quite I don't know the ratio of the nuclear medicine physicians and radiologists here. In my country, it's 1 to 10. We just came to 300, and the look around radiologists, they are already 3,000. Okay, the same here?
Yes.
Yeah, 1,000.
We are 7,000.
700.
Just 7,000.
700.
7,000?
No, 700.
Both of them are eligible.
Okay. They have used they have popularized the use of the RECIST. There are many, so they help every day the medical oncologists, surgical oncologists. So that's the reason. And fortunately, we have a very good nuclear medicine physician who has been trained in St. Louis and who has been in the Johns Hopkins for a long time, and came back to the chairman of the Mallinckrodt Institute of Radiology of Washington University, and again, he just popularized Richard Weil, persist response criteria in solid tumors. Even though the size did not change, we can just use the PET uptake, surrogate endpoints, but the final point is, of course, survival and quality of life. Okay? And we cannot do experiment with humans, so we do use the experimental animal, and we want to find the survival and tumor control probability, and also tumor growth delay. That's kind of a modeling. And we know goal and its surrogates. That's the current situation. And back to the molecules again. Small molecules. So do we do the active targeting? Yes. But you might not just kind of pay any attention to this kind of difference between those three molecules. You know, glucose, when you were in first year student of the medical school, you might need it to memorize the hydroxyl down, down, up, down, something. That's glucose. Okay? Down, down, up, up, it's galactose. Mannose, oh, I cannot. So it's just one is over there. However, those molecules, it's just glycoside ring is the same. Just the difference is the up and down of the hydroxyl residue. But glucose seeking brain and heart and tumor, galactose seeking is hepatocytes. That's the reason why his the MSA. MSA?
Yeah, MSA and GSA.
GSA, yeah. Galactosylated the albumin. Albumin has a galactosyl the residue, then the galactosyl residue is leading the albumin to be taken up by the hepatocyte. So that's a hepatocyte imaging, so galactose. And if we put mannose on the surface of the albumin, then once injected, it is readily taken up by the macrophage. So that's the story. So that kind of active targeting, so we need to just so that's fluorine labeled galactosyl neoglycoalbumin here, 2009, and gallium-68 labeled neogalactosylated albumin, 2015. Still, people, our chemist colleagues, they are studying very hard, and gallium-68 labeled mannosilated albumin here, it's just taken up by the copper cells and the spin. Then second one, the biomacromolecules here. We have natural peptides. So natural peptide was somatostatin, and they have was it Roche? They have changed it into Sandoz. The Swiss company Sandoz has just to kind of change it a little bit. So at first it was called sandostatin, and then it became octreotide. Octreotide a little bit the transformed form of the somatostatin. That's natural peptide. And finally, since 1976, once the producer of the first monoclonal antibody won the Nobel Prize, it was 1976. How I remember it was the first pre-med years. So I entered to the pre-med the college. So at that year, the Nobel Prize winner was yeah. And then since then, they have they produced many monoclonal antibodies with the MOMA, mouse monoclonal antibody, ZUMA, humanized monoclonal antibody, CMAP, chimeric monoclonal antibody, and MUMA. It's interestingly MUMA is the human. So those absciximab is chimeric. Trastuzumab is humanized. So we can just identify by the tail. Anyway, and even their fragments. And recently from Camel, so nanobody. Camel antibody is very small. And even Scientific American is explaining the antibody of a camel or llama. Please do not call it llama. That's Latin, Spanish, LLA, llama. Okay. Or we adapted his product at the Tokyo University chemist. He made a non-natural peptide, just kind of a macrocyclic, or instead of the natural amino acid, the natural amino acid is D4. Yeah, and the alpha. Natural, yeah, alpha. So natural glycoside is D4.
Yeah, glucose is different.
Yeah. So always confusing. If I take an examination of first the graded student and say biochemistry, I would fail. So I would just kind of write down the answer. Please look at the Wikipedia. Why do you ask me to memorize this? It's all in Wikipedia. So anyway, that's human met ectodomain. He made this kind of, and he gave us to us. Then, and we just did some biological study or antibody by the Swedish group, and aptide. So leucine-rich one. John is a Korean chemist, a biochemist working in KAIST, Angewandte Chemie, or the aptamer. It's just kind of a nucleic acid form. the people are doing the selective selection process by using the evolution scheme. And albumin can be considered as the macromolecule. But interestingly, my colleague, in the next door, Dr. Kang, he's insisting that the albumin is a nanoparticle. But I say albumin belongs to the biomacromolecule. Which one is correct?
Both.
Both. So yeah, so he is doing that kind of a Solomon because he's right next door. Dr. Kang is right next door. If we fight together, and so that's the size. I'm going to introduce this gold nanoparticle. And anybody is like 100, I did not care before I started this nanomaterial research. I did not care the size of the antibody, their molecular weight, but after doing research with this, I became interested in antibodies 150K. And size is 11 nanometer. And albumin is a little bit smaller. And iron oxide nanoparticle here, and you just connect with iron oxide particle. And this is peptide here. That's aspirin. So that's the dimension. How did I draw this? No, I just kind of download from blog. Everything is in the game. And that's the one here. John, Yang, So, Jung, Kim. So there are more people with the last name other than Kim and Lee. So Kim and Lee are on the street. The other people are doing research. It's overlap. So here, quantum dot is consisting of the cadmium. So one cadmium was their light yield was so small. So my colleague in the College of Engineering, they made this kind of chocolate type of. This picture reminds you of the chocolate, Italian chocolate. Yeah. So, and just to make this, and quantum dot embedded silicon nanoparticle is quantum dot square, and iron oxide here, or a conversion nanoparticle here. The constituents are the lanthanized. So here you have which line is lanthanized?
Oh.
Yeah, this one?
Yeah, that last time is described in the...
Yeah. Or here, the surface length Raman, so the kind of a surface feature is going to give a spectroscopic signal, which can be quantified. So, and upon that, the fluorescence dye was, and it was reported in scientific research again. And, you know, that's only for in vitro use because of cadmium. And it's also in vitro or in vivo topical for endoscopy. We tried. And also only here, iron oxide and conversion nanoparticle could be used, but a conversion nanoparticle we could use only for small animal study, but iron oxide, if it is successful, it can be used for. But please be reminded that when you use the iron oxide, you need to use sometimes 6 grams. Okay? Are we willing to collaborate with the radiologists or the scientists and radiology? No, I don't think so. So Professor Yun-Sang Lee is doing the research with iron oxide. It's supported by the company. But after the labeling here, radionuclide with iron oxide, then finally we are going to be confronted with the problem of how many amounts of the iron oxide are going to be given. to humans. Okay? So please be reminded. So there are the small molecule and macro molecules and nanomaterials themselves. However, when the nanomaterials themselves do not act like a targeting ligand, you can modify on the surface. The iodine 131 is targeting thyroid. Technetium pertechnetate is targeting thyroid. But if technetium does not want to go somewhere we want to send them, then we just label with a decider or hepatocyte, like that. So nanomaterials passive delivery or nanomaterial having the above surface. So all those armamentarium are in our hands. If we just put nanoparticle, then we are going to make. Now I'm going to explain the achievement. The sole genius of my department. The next to my three rooms next to me, Professor Jung. Professor Yun-sang Lee is the mentor. Professor Jung, Jae-min Jung. He looks like a genius and behaves like a genius, and he sounds like a genius. Okay. So someone is look like a genius, and some look like sound like a genius, and then he's a genius. Okay. So he made this kind of tactic using the PEGylation and also antibody and the aptamer RNA or the whatever molecule, and we called it as a encapsulation. So I'm going to explain a little bit later. So that's a game. And this is a kind of a simple summary of the current situation. So all of you jumped into the endeavor to solve this problem. Current situation is many different tumors awaiting still nuclear therapy care. For the last 50 years, we did just only thyroid cancer treatment. It's kind of the moral hazard, as I call it. We have very good the methodology, but please don't blame me. I did not do my research on tumor. I was in the field of the heart, and then moved on to the brain. Please blame me about the slow progress of the brain studies to be used clinically tomorrow morning. After I just explained, I'm one of them, but many intractable tumors. And another one is wasted efforts to optimize imaging agent and therapeutic agents separately. That's the problem. We have limited resources. Why don't we just do it at the same time? So that's called Theranostics. So I just published a book recently. Already the 5 months passed in July. Springer, and I emphasize in here that combined nuclear and nanomedicine. Nanomaterials are going to be labeled with the radionuclides. Then we can use the amount trace, not microgram, just less than 30 nanomole. Okay, and using the radionuclide, we can do the tracer kinetic for therapy and imaging. And so that's the reason why we need to understand tracer kinetic by so many equations. Are they lovely? So the Dr. Asmar just after Professor Jae-sung Lee's the presentation talk, so complicated the lines of the equation. It seems to be very lovely to me. So that equation is saying everything. So without the blah 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 of sentences. So he made me during the last 20 years to just get fond of equation rather than the sentences. No, he is doing research I'm the interpreter, kind of a translator, to understand what he had achieved, and then understand, and then explain in plain language. So that's what I'm doing. Professor Zhang did the research with Professor Lee, and I understood the meaning of theirs. So I could just kind of had a contract with Springer to publish it without their names as editors. They are inventors. I'm the editor and interpreter and translator. So if I say, yeah, that's my research assistant, Professor Zhang. He even, not nanomore, in this animal, using Professor Zhang's method, encapsulated the surface of the nanoparticle, in this case, upconversion nanoparticle, that's inert one, using that one. And copper-64 was labeled. However, ingeniously, we just changed the molecule by just not copper-64, copper-63 is a stable isotope. By adding copper-63, we increase the amount of, actually, amount from here to 1,000-fold. And those 1,000-fold, is there any difference between these animals? Somebody has, then can I say that it's the same? Why? It's because you are seeing the same gallbladder here. It means that hepatobiliary excretion is going on with any amount of, so with 50 picomole, we were worried about the pharmacological effect of those nanoparticles. So we decreased down to the 1,000-fold. Okay, just like a 1/1,000,000th of 1,000. So it's the same. That's the trace amount and the tracer principle works. So tracer principle, if tracer principle is working, then we can apply tracer kinetic to understand the biodistribution, and finally dosimetry. That's our strategy. Oh. Yeah. And back in 4 years ago, I found the strange phenomena in the literature. So chemists or chemical engineers, they publish paper, and they see the liver uptake here, and they immediately say that liver uptake is by copper cells. However, in liver, copper cells, how many percent of the liver are occupied by copper cells? So I became curious. So actually, we are the liver scan expert. 20 years ago, we did a lot of liver scan and thyroid scan. Now we don't do that. So nuclear medicine is changing decade to decade. Okay? So in liver, there are, simply speaking, more hepatocytes than copper cells. Simply. So I wondered why after 2 days or 3 days, spleen uptake is there and liver uptake is gone. What happened? Here, or some others, and 2 hours, 24 hours, there might be the kind of a difference between the color stripe, but they said 20% ID per gram and 2 hours, and using the same color stripe, that it means that here and here, and here, tumor, however, the lung and liver, spleen, and nothing. So here, so that was the one group of subjects. However, they are like this. 2 hours, 4 hours, 8 hours, 24 hours, and we could just see here, gallbladder and the intestine. And at that time, we used the upconversion nanoparticles labeled with copper 64. Copper 64 gave us this kind of image, and the upconversion nanoparticles, they gave this capability of the imaging in vivo in situ luminescence imaging. They call it luminescence imaging, and which measure the quantitatively, and we could find that 80% of the nanoparticles are passed away. I mean, not passed out via hepatobiliary excretion. This kind of characteristics of the some nanoparticle surface modified one were estimated in the literature, so we could just find. And even we collected feces. You know, have you heard about the feces test? It's a dung test done by Dong Lee. And that's a single one upconversion, the luminescence imaging. Okay. And while publishing this one, someone from Germany had published this, and like this one, and they used this kind of amide bond here. We used by the ingenuity of the Professor Jung, thiourea. No, so we could see that the upconversion nanoparticle is the emitting luminescence, the quantitative amount of the luminescence and also the surface radioactivity were the same. It means that integral, the particle is excreted via hepatobiliary system, but interestingly, their system, indium, and the gold nanoparticle, the gold 198, those nanoparticles were recovered differently. So they correctly concluded that the capsules are disencapsulated, and it's then our trace principle is failing. And interestingly, in the same year, our paper was published in the scientific reports. We sent them to Nature Nanotechnology, immediately rejected, and we found that at the same year, German group's paper were published in Nature Nanotechnology. Without our paper, they would have just kind of denied the tracer principle of the encapsulation method. Capsules are detached and with the radioactive material there, and if you follow the capsule, then you are not following the particle. So that was their conclusion, correct conclusion. But ours were different. So in the literature, we have two different ones. Those two different ones have different the linker there, bond. So those two, copper and indium, and we could find here many hepatobiliary excretions, also in the literature. So we would be happy. So we have become interested in the excretion via somewhere. And you found that the PRRT, they are killing kidneys. So in addition to liver, and kidney is the area of the excretion. And in Nature Review Materials, or our book's chapter, written by the Dr. Im. And then we moved on to pay attention to another nanoparticle here, ceria. Ceria is cerium, so you might find here. Ah, yeah, that one, cerium. Interesting property of the valence 3 and valence 4. By changing the 2 and 4, they act like catalase inhibitor. Anyway, the reactive oxygen species scavenger. So it can be used for treating subarachnoid hemorrhage or intracellular hemorrhage, or even sepsis. So in animals, now they are going to just kind of transfer their, my neurologist colleague, another Dr. Lee, yeah, oh yeah, Lee and Lee. So those leads are studying very hard, and Kims are working. No, he is not Kim. Okay, on the street. Okay, so we labored by his effort the Syria with Nota and India, and did this kind of research. And we are still working on that. And this is not all. Actually, we are experts in physiology, but once something is injected, immune system is immediately responding. So since several years ago, I started to learn immunology again. It was really painful. Immunology had advanced because I had been in endocrinology, and also I majored in Graves' disease when I was a PhD student back in 1990. I learned a lot about the so after 30 years, I tried to learn 25 years in nanomaterials immune system and by which cells. So they have been changed. Monocytes are making macrophages. That's kind of a classic theory. No. So tissue-resident macrophages from birth, they reside there. The representative ones are microglia here. They are staying there. They are different from the monocyte-derived macrophage. So what about the liver? Copper cells are the famous tissue-resident macrophages. Monocyte-derived macrophages are tissue in spleen. And that's one. So there might be two types of response. The immediate one, non-specific one, is innate one, and adaptive response is kind of a B cell and T cell related one. And this is well known. Immunoglobulin M is developing against the. However, interestingly, there has been changing. You know, the innate immune response can be trained. I mean, the second injection is higher. This was published in Science. And so that's the current situation. Innate immunity can be trained how? By epigenetic modification. Things have become so complicated. If you are going to inject something new to the body system in mouse or in human, then from that day, we need to learn immunology seriously. And the immunology is changing every day, almost every day, based on the single cell omics study recently. So one person cannot do all the things, so we need more colleagues, and that's up to the next generation, and you are the next generation. These are the serial nanoparticles. Here, Angewandte Chemie, the applied chemistry. Here they have made this one, and they could just inject them and could treat Parkinson's disease. Oh no. Parkinson's disease. Where is it? Okay, this is the last slide. And also, they have made the Alzheimer's disease model, and using Celia, by just removing the reactive oxygen species, they could treat Parkinson's disease in a mother or Alzheimer's disease in a mother. But how? I paid my attention to the how. They did the stereotactic injection to the brain. So it cannot be translated to the clinical situation. So what should we do? So we need to just inject it via circulation, I mean intravenously. Then intravenously, the injected new novel materials, nanoparticles in addition, as well as the nanoparticles, every new one is going to circulate and distribute to the body and they need the, not small molecule. Small molecule can act as a peptide. Yeah? So, but anyway, they need innate and adaptive immunity. So, you know, there is a rumor that many monoclonal antibodies are working at first injection, and after the second injection, they are kind of injecting the monoclonal antibody against tumor, just without any confidence, just to make sure with a kind of full of hope without any scientific background, because they already at first injection immunoglobulin G, M or G had developed, and they are going to make an immune complex about with the second injected monoclonal antibody second time, then it is not going to work. So once in a lifetime, however, the pharmaceutical companies are selling, and the medical oncologists are just kind of adopting second and third, and patients are going down, and no more. If patients are have been dead, then they stop. Okay. So I try to expand the material to include the new one, because the China, Singapore, Korea, and the advanced countries, they do just to kind of expand. And there are many things to solve. Okay. And this is the method that Professor Lee, the RI, radioisotope pre-labeled chelator, with a click reaction, bio-orthogonal one, with nanos. So it's just kind of nanos, and the click cover RI pre-labeled the ligands, and they just mix, and then vortex, and then just to kind of size exclusion chromatography, usual one, and just kind of push, and then inject. That's his idea. Okay. As I told you, I just behave like the honest and sincere interpreter of the Professor Yun Sang. His avatar. Oh, I used some more time, so we have. However, do you have any questions? Then please ask Yun Sang Lee. Yeah, one question.
How to establish such kind of labs?
Pardon?
How to establish such or start such
Yeah,
kind of labs?
okay. At first it takes time. 10 years. Okay. And then we apply many the projects. Usually the success rate is 30%. 3 application, 1, and include in that project to buy the animal pet. When I was in charge of my department, I bought animal pet. At first, it was $600,000. Because of the financial crisis by the United States of America, there was a kind of exchange rate has jumped. I paid finally $830,000. Wow. Anyway, I installed the first. Yeah. So please pray for the global economy should be stable and apply your project.
Michael, I think it will take not so long, because we have already made a kit for radiolabelling of each nanomaterial. So if you want, yeah, that's a way. So there's no problem for nanoparticle and also labeling. Just so you can apply that thing into the different particles, such as other peptides like that. If you have an animal.
So first we need to get
At first, you don't need the animal. You just use the animal case. Animal case. So 20 years ago, we did like that. We just purchased. Why? Because there is no regulation. The genius, our genius, the Zheng, kept his animal case just in his next room. Someday, those rats escaped. Mice escaped. In the operation room, the janitor found him and just brought him and delivered it to Professor Zheng. Under the current regulation, he would have been fired. But at that time, there was no regulation.